Mayank Sharma sir to give me the opportunity to interact with this team gathering, and he means 2 days back I got an invitation, and I thankfully accepted it, and now I'm going to start my discussions on the topic which I think, okay, let me share first. Okay, I think my PPT is visible to all of you. And the topic which I have chosen for this particular discussion, today's session, that is the application of the CFD in hydro turbines field. As introduced by the Raghib, I have been associated in this field from the last 5 to 6 years. I have done my PhD in this hydro turbine sector, and I have implemented this CFD tool for the designing of the hydro turbine component. So here you see there are two important word in this particular topic is one is CFD and one is hydro turbine. In this particular faculty development program, I have seen that one of the session is being engaged by some eminent scholar, and the topic is Introduction to CFD. So I think the detail of the CFD and their background, mathematical background, that will be discussed in that particular session. And but here I would like to basically share my experience in doing the CFD in hydro turbines field. So here the most important thing is, first thing we need to understand what is the CFD and what is the hydro turbines. Most of the people in this particular forum, they are being associated with the mechanical engineering department. So most of you people are aware about the hydro turbines. The hydro turbine is a device which is being used to extract the potential energy of the water, which is available in the form of net head, and this device basically converts the potential energy into the mechanical work. So here what is important means, once you are designing a hydro turbines, the very important parameter which we take into account is the efficiency. That is the first thing in the point of view of the performance. So that efficiency is basically the mechanical power divided by the total available energy across the turbine. So the mechanical power is basically the torque into omega, that is which is being converted into the electrical power at the end, and the incoming power which is available across the turbine, that is rho GQH in the form of head and discharge. So that is the function. So basically in hydro turbines we have already studied in the BTech course, that is two kind of the turbine is there. One is impulse and another one is reaction. So in the impulse turbine we basically studied Pelton, and in Francis we generally go for the Kaplan and the Francis in reaction turbine. But there are so many other kind of the turbines is also being used for harnessing the hydropower. That is some kind of the means hydrokinetic turbines are there, cross flow turbines, turbo impulse turbine. So there are various kind of the turbines is there to basically the harness the potential in the level of the micro and the mini hydro schemes. Means conventionally we use three kind of the turbines, that is Pelton, Kaplan and Francis, but unconventionally for the lower potential we basically go for the so many kind of the turbines technology. The second important thing is here, what is the CFD? So here the CFD, you already know that the CFD stand for the computational fluid dynamics. So there are again three terms. One is what is computation, what is the fluid, and what is the dynamics. So the computations means we are basically going to solve the some of the governing equations which is being developed in the various phase of the fluid mechanics development. Like you already know, there are so many equations are there, and so many empirical relations are there, like Bernoulli theorem. You already know the Navier-Stokes equations, and there are different kind of the fluid dynamic equations which is available. In some cases, we basically incorporate the viscous forces, and some cases we basically don't include the viscous forces. But if we see the generalized fluid dynamics equation, that is basically the Navier-Stokes equation. And that Navier-Stokes equations, once we see this equation in the transient flow condition, this equations looks very complex. And that particular differential equation is the second order differential equation, where the unknowns are more than the equations available. So you have also known this, that once the unknowns are more than the equations, we basically follow the numerical method techniques. In some phase of the mechanical engineering courses, we have we basically go through this subject also, numerical methods, where basically what we do, we basically decompose the differential equation into the algebraic equations, and once it is decomposed, that algebraic equations basically solved with using some numerical methods like Jacobi method, Runge-Kutta method, and so many kind of the methods are there, where basically we do the iterations. Once the solution is converged, we say that this is the final solution, and that particular means value we can assign for a optimum value. The same thing we do here, but the thing is, we do this thing using the computer, supercomputers, or you can say the workstation. Because once you solve the very simple example of the fluid flow by using the numerical method, generally we follow the one-dimensional approach, where we basically decompose, discretize the differential equation for a one-dimensional form, and then we just go for the solution using the numerical methods. But the thing is, once the problem is three-dimensional, means ijk, so there is no alternative to do the solution using some using manual. So we have to use the computer facility for that. So that's why this computational fluid dynamics equation, basically we are going to solve with the computational power. So that is the meaning of this. So, but the thing is, once we go for the CFD simulations, one thing is very important. We need to validate your CFD result with the experimental result for some reference cases. That is a very important point, because without validations, the result of the CFD has no meaning. So suppose if you are going for the modification in some geometry in the hydroturbines or in any other area, specifically I am talking here with respect to the hydroturbines, but the thing is, you can use this CFD for any fluid flow problems, for solar, for any kind of the gases, any kind of the steam turbine compressor, everywhere you can use the CFD. Where there is a flow, there is a CFD. That is a thumb rule. So in any thermal related problem, you can use the CFD for basically for a prediction of the performance, for a optimization of the geometry, also for other aspect also. So that's why this CFD is nowadays CFD is very important tool for basically analyzing the fluid flow, for predicting the performance, and for optimization of the profile. So broadly, if I categorize the role of the CFD, so basically three category we can do the simulation. One is for performance prediction, one is for the flow analysis, and one is for the design profile optimization. Okay, so now basically in the CFD, basically we follow the control volume approach. So you already know there are two kind of the approach. One is the control mass approach, control volume approach. CFD basically we follow the control volume approach, where we basically model the fluid domain, and that model is being discretized using the meshing approach, where we basically decompose the particular model into crores of the mesh. Like suppose if you are interested, I just take example, if you are interested to simulate the airflow in a room, so first thing you need to do, you have to model the room first by counting where is the window, where is the door, and the other kind of the, and also you need to provide the what kind of the wall property is there, and what is the inlet condition and what is the outlet condition. Then you define the boundary condition and you get the velocity profile or the temperature profile or whatever kind of the parameter you are looking, you can just find out. But the first thing is you have to model the room. What is the dimension of the room? First, you need to make a 3D model of that particular room by incorporating all the details. Once the room is being modeled, now you have to decompose this room into n number of the small domains, and that small domain is called the mesh. I will discuss these things in the subsequent PPT, but just I would like to share the idea what we do basically. So then we need to decompose the total volume into n number of segments, n number of smaller volume, and that smaller volume is called the mesh. Once you do the meshing, then we go for a boundary condition, the kind of the equations which we are going to solve. Like in the fluid flow, we basically solve the Navier-Stokes equation. In the heat transfer application, we have basically the Fourier equation, some kind of the differential equation you solve. So based on your requirement, we basically choose the which kind of the analysis which we are going to take. Whether we are interested in the thermal profile, then we have to open the energy equations also. So in some cases, we are not interested in the thermal profiles like hydro turbines. There is no meaning of the temperature variation across the fluid domain. So we are not interested in the thermal profile, but we are more interested there in the pressure and the velocity distribution. So once these velocity and the pressure distribution we got across the domain, then we can evaluate the secondary parameter like efficiency, torque, power, and all whatever the value which we are looking. So that thing we get from this after the equations are being solved using the computational facility. So this is the whole picture of the CFD. Now I'm going to share. This is the hydraulic turbine which is being laboratory, which is there in the IIT Roorkee, and there is a model test also. So in order to design the hydro turbines at a prototype condition, prototype level, first we design the turbine using CFD. The first step is CFD. Once we are satisfied with the proposed result which is being provided by the CFD, then we go for the model fabrications, and then we validate our CFD result with the model result obtained by the experiments. For the model testing, we have a dedicated IC code where a lot of the modern instrumentations we basically use there in order to get the sufficient information, and based on that information we basically predict the performance. So now the second step here is to basically validate the CFD result with the model testing results. Once we are we are satisfied with the model result that this particular design is going to work in that level. Suppose nowadays we have the hydraulic efficiency of the turbine like above 90%. Even some of the turbines, Francis turbine, basically we are reaching up to 94 or 95% also. So basically these things we basically first verified with the model results, and once we are we are guaranteed that this particular turbines will work uh, that level at the prototype condition, then only we go for the fabrication of the prototype. And once the prototype is developed, then we basically install that prototype at a particular site. And then again, we need to do the this performance test after the installation, and then we verified the result. So this is the basic procedure which any turbine manufacturer basically followed. But the first step here is to do the CFD analysis. So basically, what the advantage the CFD analysis have, because this is a virtual simulation, so there we don't need to install fabricate any kind of a thing. We can simulate n number of the models. And for your information, I can share one thing, that the model testing cost basically ranges from 50 lakhs to 1 crore. So that kind of the cost is involved at a model level. So nowadays people are basically going for the CFD analysis so that they can bypass the model testing at some level. And the second advantage using CFD in the hydro turbine is, in the CFD, we can basically simulate the n number of models, n number of cases, which is not possible once we follow only the model test. So that is the second advantage we have. And for your information, one thing I can share, at the prototype level, the cost of 1 megawatt plant, hydraulic plant, that basically ranges from 5 crore to 7 crore. So if we are going to develop the 100 megawatt hydraulic plant, so basically we investing the 700 crore rupees for that. So if something is being happened once the prototype is being fabricated and installed, we cannot revert back because a lot of the money is already invested. So we have to make sure that whatever we are basically predicting through the CFD result and the model test result, that need to be very precise. So that's why in the model test, basically we follow the IC code, which basically gives the uncertainty in the efficiency value within the 0.25% error. So that kind of the precise value basically we get from the model test result. Once we are sure that this turbine is being performed at a such level at a prototype condition, then only we go for the prototype installation and prototype fabrication. But the first step is we need to carry out the CFD analysis. So here I can the point is why the CFD is very much important in case of the hydro turbines, because a lot of the money is being at stake. So that's why the CFD need to be performed very precisely and accurately. Nowadays, the CFD codes are well developed in this particular application. Even at a best efficiency point condition, we can achieve the accuracy of 0.5%. Means we are in the 0.5% plus minus uncertainty. Means suppose CFD is predicting the efficiency, suppose 92%. And if you have followed the proper guidelines of doing the CFD and well-established methods, then you can claim that your result is within 0.5% error. So that kind of the confidence we get from the CFD once we follow it accurately. Okay, so what is the process here? First thing is, first we need to make a geometry. Then we have to define the physics. Physics means what kind of the differential equations we are going to solve. So in case of the fluid flow problems, we basically solve the Navier-Stokes equation, Navier-Stokes equations coupled with turbulent model. There are so many turbulent model is being proposed by different researcher. One of the famous model here is K omega SST. So once this equations K omega SST, there is two equation. One is turbulent kinetic energy equation and another one is the eddy dissipation rate. So two equations basically being added in the Navier-Stokes equations. Then only these equations are being solved with using the computational resource. The next step here is mesh. Then we basically decompose the domain into n number of smaller domain, and that particular domain is called a mesh. And then we solve the particular Navier-Stokes equations, and then we can see the contours and whatever the parameter you are looking at different points, you can extract from the result. So this is the process we follow in the CFD. But CFD is not very much, CFD is not a tool which is limited to the hydro turbines. We can use this particular CFD for any applications where fluid is involved. Aerospace, marine, combustion, multi-phase flow. Like a cavitation prediction, we basically use the multi-phase flow model. And combustion also we have some models. And aerospace, we basically see the drag and lift and what is the things are there. So basically the CFD we can use in the designing of the cars also, like sedan geometry, you heard this. That is the geometry which is very much where the drag force is very optimized. So that kind of a thing we can perform using CFD and we can get the optimum profile. Now, moving next slide. Here you see already I've discussed. First thing is we have to define the problem. Then we have to define the equations. Then we discretize that particular equation using the meshing. And then geometry is formed and the mesh is being generated. Then we have to follow the computer programs, then simulation result, and then we get the results, and then we can compare that result with the experimental result. And once we validate our CFD result with the experimental result, we get a confidence of the CFD code. Once we have the confidence, then only we can use this tool as a independent tool for designing the further, for designing the profiles. But first thing is we need to validate with our basic model, basic CFD result with the experimental values. So that is the prerequisite of the CFD tool. First thing is your CFD tool need to be validated at some level. Once you have a confidence in your CFD codes, then only we can use that code as an independent tool for a redesigning of any profile. That is the prerequisite of this kind of the application. Now, why we use the CFD? Although we have a experimental well-defined facility at the model facility we have, means model testing we do, but the advantage of the CFD has here, we can analyze and design the thing. That is the first thing where we use the CFD for designing and analyzing your product. Suppose if you are fabricating a steam turbines, then first you have to analyze the flow there, and then once you hydraulically your profile is good, then you go for the second step, that is the mechanical design. First thing we do the hydraulic design, then it is a mechanical design. So first we have to see what kind of the profile is giving the best result. That is being basically extracted, that is being extracted by the CFD result. So we can predict it by using the CFD result. Now, simulation based design instead of build and test. What is meaning of this? Suppose if you have 100 models of any design, of any component. So if we are going for the model test, you have to do the model testing of the handed models. Once you do the model testing, then only you can get the feeling which model is basically giving you the best result. So it is very much time consuming, and it is also very much it is not a cost effective solution, because one model test is basically in the hydro turbines, it costs 50 lakhs. So we cannot follow that route. What we do, first we have to do the CFD analysis. There, after doing the CFD analysis, we can get 2-3 models which you think that may be the optimum model, optimum profile, you can say. So only the what we will do, we have only 2-3 models which we can easily go for the testing, and we get the best one amongst these 2-3. So that kind of the advantage we have using the CFD. We can do the virtual simulations again and again without investing the cost, and the time requirement is also less compared to the model testing time requirement. And also it is a cost-effective solution, more rapid compared to experiment. In one experiment, in model test experiment, it requires 3 months. And in 3 months, using CFD, you can test at least, depending upon your computational facility you have, you can at least do the simulation of 10 or 12 or 20 turbines. So it is a cost-effective solution and more rapid. CFD solution provides the high database for investigation of the flow field. What is the meaning of this? Suppose if you are interested to investigate some parameter like pressure or stress or some other pressure recovery, any parameter, if you are looking, you have to install a sensor for, in case of the, if you are doing the experimentation, you have to install a sensor at that particular point. Then only you can get the information at that particular point inside the fluid domain. But using CFD, you can get the information at any point and any parameter. Whatever the flow parameter you are known, any flow parameter value you can get at any point. So basically CFD gives you a high database to analyze how the flow is being, what is the behavior of the flow inside the fluid domain. So you can get the more insight for a flow field condition inside the fluid domain. So CFD provides the high database. The fourth advantage you can see here, the simulation of the physical fluid phenomena that are difficult to be measured by the experiment. Suppose you are doing some combustion analysis where it is very difficult to go there and in that particular atmosphere and you install the sensor there. If it is not possible, then there is only one choice, that is the CFD. So CFD has no barrier. CFD can predict the temperature up to 10,000 degrees Celsius, but actually it cannot be, you cannot get through the experimentation because some material constraint. So that kind of the facility we have using the CFD. And the last one is knowledge and exploration. You can develop the knowledge, how the flow physics is being changing inside the fluid domain. So these are the advantages we have using the CFD over the model testing. Model testing has limited information. Using model tests, you can test the limited models. So basically first step is we use the CFD. Once we are satisfied with the result, then we go for the model test to verify that particular result. Okay. Now, comparison wise, we have already discussed the simulation less expensive, experimentally more expensive. In this thing, I am talking with respect to the hydro turbines. In other particular area, This the situation may be reversed, but I am specifically talking with respect to the hydroturbines related field. Scale may be anything. Means simulation, you can make a fluid domain ranging from the kilometers to the millimeters, but experimentally it is not possible. You cannot model, you cannot do the experiment of the 1 kilometer means runner diameter. No, but the simulation, any kind of the scale is valid. Then information wise, you have all kind of the information, but the experimentally you can get the information only where you are in. Now, I am just basically before going into the hydroturbines details, first I would like to show you the example how we do the how we plan the strategies, CFD strategy. One thing here I have, you can see there is a one example where there is a rectangular channel and one sphere is being put at a center. So first we need to see what is the flow distribution there across the sphere, and this sphere is one case, this sphere is being stationary, and another case I will show you once this sphere is being rotated. But the first thing is you need to model the both thing, this rectangular channel and the sphere. Then what we have to do, you have to subtract this sphere from the rectangular channel, because we need to make a 3D model of a space where the fluid is flowing. We are not interested what is happening inside the sphere. No, the volume where the flow is being flown, that volume is only need to be modeled. That is the first thing. So most of the beginners, basically they do this mistake. They model both the things, but we have to see the volume where only fluid is flowing. That is the first thing. Then once you do the model, then we go for the meshing. Then we make a mesh. Here you see this particular 3D space is being divided into n number of smaller mesh. Okay, now this figure you can see the quality. So here this is the unstructured kind of the mesh. I will discuss what is the difference between the structured in the later slides. But you can see this is some tetrahedral kind of the mesh, which is called the unstructured mesh. So here you can see the quality, because the quality is also important criteria here. You need to make a meshing in a such a way that we have sufficient, we should have the sufficient quality of the mesh. Because if the quality of the mesh is not good, the result which is predicted by the CFD simulation, that will not accurate. So the result of the CFD analysis is more dependent upon the quality of the mesh. So that's why the meshing is the art. So you have to make a mesh in such a beautiful manner where you can get a very good quality of the mesh. Quality wise, there are 4 or 5 parameters which we need to look. One is aspect ratio, one is the skewness, one is the orthogonal quality, one is the expansion factor. So these are the some parameters by which we can say whether the mesh is good or mesh is wrong. So generally in the unstructured mesh, we see the skewness and the aspect ratio. So in the guidelines, CFD guidelines, although it is not well established, because the in the CFD there is a no IC kind of the course. So for a different applications, there are some sets of rules that for this application the quality should, the minimum quality should be within this range. For that kind of the applications, we can go for the higher or lower limit. So, but the thumb rule is the skewness should be less than 0.8. That is and orthogonal quality should be more than 0.2. That is the things. Depending upon the different application, this value may change, but the range, the minimum that need to be checked. So once you see here, after subtracting this sphere, we have this kind of the section where we have applied the boundary layers. Here you see, this is the boundary layers. So these things we have to make once we are applying the fluid flow equations. So once you do this, now we apply the boundary conditions. Suppose what is the, whether you are going for the gravity effect or not, then we can select the some kind of the turbulent model here, SSTK omega, some viscous model we can select. We can define the inlet velocity of the air, outlet, and what is the condition at the wall. So these are called the boundary conditions: inlet, outlet, and the wall, and what kind of the turbulent model you are going to pick, and other information like whether we are allowing the gravity to be incorporated or not. So these kind of the boundary condition we need to provide before starting the simulation. Then here you can see these are the result. You see, once the air is, this is the inlet and this is the outlet, this is the outlet. Here you see, once the air is hitting on this sphere, the pressure is increased. That is called the stagnation pressure, where the velocity is zero. Here you see, the velocity is zero in this range, and here the maximum velocity we are getting. So there you can see there are chances of the separation at this particular point, and again there is a wake formation after this region. So this way you can see the, using CFD you can extract all the information, all the fluid flow information once the results are with you. So I have plotted this result in the form of pressure and the velocity, but you can take any flow parameter, whether it is turbulent kinetic energy, dissipation rate, pressure, total pressure, then different stresses also, forces also, whatever you like you can plot and you can get the information. So this is the case where the sphere is stationary condition. Now the second case, this kind of the streamlines also you can see that here the velocity is more. So vector also you can see, and at what particular location, what is the magnitude of the what is the magnitude of the velocity at that particular point. So all the information you can get using the CFD result. Also you can get the values across any curve, and you can plot these things and you can get the information. Now this is the comparison between the stationary and rotating sphere. There you can see the stationary condition. When the sphere is stationary, you can get the maximum velocity is here, and the region you can see here, that is something like that. But once the sphere is rotating with this direction, you can see the region is being shifted here like this. So all the effect you can see what is the new values at different point you can extract, and you can see where the where the inflection is being happened and where the wake formation is there, where the separation of the separation phenomena, all the detail you can see using this. So this way, this you can use the CFD. So this is the one case I have, you can see here. Now I just focusing my discussion on the hydro turbine field. There you know the condition of the flow in the hydro turbines is very complex. Very complex means because there is a rotation of the runner. Runner is being rotated like a 1000 rpm, 2000 rpm, 3000 rpm also. So this is the very, the very stability wise, this is not a good stable flow, because the rotor is rotating at a very high speed. So we have very unsteady kind of the conditions we have across the turbine. Reynolds number is very high, like you already know. Any flow which is associated with the water, that is 99%, uh, that is being categorized as a turbulent flow, because the Reynolds number is always very high there. So in the turbulent flow, the the flow will be very unsteady and the transient. So this is a lot viscous force we need to account. The fluid is incompressible because the velocity inside the turbine is less than 20 meter per second. So that this kind of the flow we can treat as an incompressible flow. Mach number is less than 0.1, you can say. Cavitations, because what happened, because rotation of the runner, what happened, there are the region where the vapor pressure drops with some certain limit. If the vapor pressure drops with a certain pressure level, the bubbles forms, and the bubbles basically hit on the surface, producing the lot of the noise and the instability to the flow. So that kind of the cavitation is not required in the hydroturbine applications, but depending upon the operating condition, there are chances that the turbine need to be operated with cavitation conditions. So we have to be sure at which region the cavitation problem is not there and which region the cavitation problem is there. So the operator should know these conditions, that we need to run our turbine at a site with only this particular operating regime. We are not going to run the turbine for a cavitation range, because in cavitations the efficiency drops. In the cavitation, what happens? The instability is there. So it is not good for the health of the hydro turbine. So, but you also know this cavitation is basically the function of the setting level of the turbine. This is the important thing. Setting level of the turbine. At what level you are going to set the hydro turbines, that defines the sigma plant. Sigma is basically the function of net head, vapor pressure, and the suction head. So your sigma should be more than the critical sigma. And once your sigma is more than the critical sigma, you are away from the cavitation condition. So these kind of the study we also perform using the CFD. So there are some cavitation models which we apply along with the turbulent model. Then we can predict at what suction condition we have cavitation and what suction condition we are away from the cavitation. So these kind of the things we can predict using the CFD. Also, we can see the dynamic behavior. Dynamic behavior means, suppose flow is there, so then that flow is the transient in nature. So it basically the stresses which is on the wall of the component. So component wise, we have 4 component casing, runner, distributor block, which includes the guide vane and essay vanes, and the last part is the draft tube. So basically we can see what kind of the stresses are there at different point in each component. So there you can suggest in the modification in the design. Suppose at some particular point the stress is more than the what you have set. So that part need to be more strengthened. Then only the life will be improved. So these kind of the thing which we can predict using CFD. Once the CFD we connect with the FSI. FSI is the new domain where we basically coupled with the CFD. with the, and this is called the fluid structural interaction. So this is the new topic where the lot of the researchers are working. So we basically connect the CFD result with the you can see the FEM, CFD plus FEM kind of thing. Then only you see we can predict the live stresses, what is happening at a mechanical design level. So CFD predicts the hydraulic performance. FEM predicts the structural performance. Once we couple these two, we can exactly have the idea of the life of the turbine. Okay. Now, some application you can see this. This is the cut section of the Francis turbine, where this is a casing. The flow is going into the casing, and then it is going inside that this guide vanes. Then it is a runner, and then ultimately it is drafted. So application wise, we use the CFD for investigation of the flow field. We can predict the erosion and cavitation. Design optimization. In my PhD work, I have worked on the redesigning of the draft tube, which I will discuss later part of this discussion. So this is also possible to redesign the flow passage using CFD. Then open channel flow simulation. Like suppose if you are modeling a river, modeling of the river, modeling of the any open flow system, then also we can use the CFD. And prediction of the hydroturbine performance. So these thing is common, which I have already discussed. Here you can see this is the Pelton model. This is a jet, and this bucket is rotating, and this is the flow around the this pressure around the pressure value across the runner. What is the need for using CFD in hydroturbines? The advantage, which I have already discussed, is reduces the number of models and measurement. That is the first thing. Gives the insight of the flow condition, which is not possible by doing the model test. For small project models, for small projects, suppose some projects, hydraulic projects is less than 5 megawatt. So they cannot bear the model test cost. So then only they people go for the only CFD solutions. So this is very good for the hydraulic turbines whose capacity is less than 5 megawatt, where we cannot bear the model test cost, which is too expensive. Then pressure distribution obtained with the CFD is needed as the input data for the stress analysis. So once we have the sufficient information through CFD, and that value, that pressure distributions, we basically take as an input condition for the stress analysis using the FSI fluid structure interaction approach. Then only you can judge the stress profile. And then CFD results are also used for a optimization algorithm, which I will show you in the next slide. What are the current research area? One is optimization of the runner and draft tube geometry. Suppose any turbine which is being installed at 40 years back, okay, which has already in expiry date, and that runner is suppose the performance of that particular plant is 85%. So once you are going for the refurbishment and the modernization of that plant, you can go for the runner profile optimization. We can propose the new runner profile so that we can get the more efficiency there. So in that area, we are basically working on. Lot of the turbine manufacturers, they are basically working on. Before going for the modernization and the rehabilitation of that particular plant, they also propose to install the new improved runner profile and the draft tube profile. So that can be done using the CFD. Analysis of the fluid flow in the draft tube, that is very challenging, and that is basically the lot of the researcher, they are working on this particular area, because draft tube is part of the component, and is very transient there. And once the turbine is operated at a off design condition, the draft tube flow draft tube analysis is needed, because in that cases vortex rope is being formed, and that vortex rope is not desirable for the operation, because this vertex rope again and again it is hitting on the draft tube cone, and that's make the structure means that structure life of that structure will be at stake. So we don't want to operate the turbine in a off design conditions where the vertex rope is being formed. So we need to do the analysis before the installation of the prototype turbine. Now people are working on the mitigation of the vertex rope, because this vertex rope is not desired. So people are using some technology like air injection, water injection, so that it basically dilute the rope. Once the rope is diluted, so stability wise, the flow will be more stable in the fluid domain. Research of the cavitation mechanism and the anti-cavitation measures. This is also a burning topic nowadays. We have to make some mechanism where we can control the cavitation. Although cavitation is the problem of the design, cavitation is a not problem of the flow. Cavitation is basically the problem of the design, because once you define the setting level, the value of the sigma is defined at that particular time. And then measurement and the control technique of the fluctuations, cavitation in the hydraulic turbine. This is also a important area where the lot of research is going on. Then the optimization of the runner profile. So those who are interested in the hydro turbines, you can select any topics. These are the burning topic where the lot of the research is going on. This optimization of the runner profile and the draft tube passage for the high efficiency. Okay, so we are basically looking to use the CFD to make the profile more hydraulic friendly, so that we can get the maximum performance. And there is one more new technology, that is pump turbine, which nowadays is going to change the overall spectrum of the energy sector. So pump turbine is basically, I can say that is like a battery, very bigger battery. What we do, we just pump the water. Once there is no demand, we just pump the water back into the sump, and once there is a power demand, we basically generate using that water. So that kind of the technology is nowadays is very common in other countries, but now India is also looking to use kind of the technology. So in that particular operation, pump turbine operation, we have to look forward to see the what kind of the flow problems are there. So a lot of the instability issue is there in case of the pump turbine. So people are working so that the stability issue can be resolved. For doing these kind of the simulations, we required a very high computational facility. Because what happened in the transient analysis, there are two kind of the analysis. One is the steady state and one is the transient. In the transient analysis, basically we predict the fluctuations also. Suppose if you are interested in the power, hydraulic power and the torque, so that value is not going to be constant. That is the fluctuations. You also see the fluctuations, and through that fluctuations you get the average value, whether it is a torque, whether it is efficiency, whether it is a power output. So these fluctuations are also very important for the design aspect. So that's why every time we do the transient analysis, steady state analysis in the hydro turbines has no meaning. For a initial guess, you can do the steady state analysis so that you can get some idea. But for in-depth analysis, we only follow the transient simulation. And with my experience, I can say that doing transient analysis with suppose we have a we have a 100 core of computational facility. So it takes 10 days to do the simulation at one operating point. So that kind of the simulation power required in case of the transient analysis. So that's why doing the transient analysis, we should have a very well computational, high performance computational facility. Then only we go for a transient simulation. Why we do the transient simulation in case of the hydro turbines? Because you know the rotor is rotating. So at every instant, the orientation of the rotor with respect to stationary domain is different because it is moving. So every instant, the pressure and the velocity profile is getting changed. So that's why the output is also gets changed. So for predicting that fluctuations, we have to do simulation at every instant. Means t is equal to 0, then t is equal to t1, t2, t3, t4 like this. So that requires a lot of the computational facility. So for this simulation purpose, this facility we use. Because in simulation also, in simulation only, we require the high performance facility. For making a mesh, for making a modeling and meshing, we don't require the much. Normal computer, your normal laptop is enough to produce the 3D model and the meshing. But simulation requires the high performance server. So that is the important. That's why with the development of the computational resources, nowadays CFD is getting more common. Because 10 years back, the computational facility was not that much of that kind of the high. But nowadays we have a good server, good workstation, and the cost of the workstation is also getting decrease and it will go on. So because of that, the researcher is basically more CFD is getting more common in the research. Okay. Now you can see for a modeling, we can use any kind of the software. So ICM CFD, ProE, ANSYS Workbench, BladeGen, SolidWorks, any software we can use for a modeling of a fluid domain. Here you can see this is a model of the casing. This is the stay vanes and the guide vanes. Then it is a runner. Then last part is a draft tube. So, but generally what happened? The turbine manufacturer don't provide the runner profile. So a lot of the reverse engineering we can do so that we can get the 3D profile of the runner using some scanners. So once the profile is not known, we can use the scanner to get the profile. This is based on the reverse engineering. Okay, and we have some we can use some software platform so that we can get the some kind of the accuracy. So this is the software that is being used for the modeling, and this is some another turbine. You can see a different turbine. So this is the model. So there are, this is a Stevens, runner, draft tube, casing. This is a full domain. First step is to do the modeling. Now, as I discussed with you, that is a type of the meshing. Now, decomposition is basically, we have to see what kind of the decomposition we are looking, whether it is structured or unstructured. Unstructured, basically, if the Smaller domain is like a tetrahedral, like this pyramid kind of thing. So that is unstructured. If it is a hexahedral, we can see this is the structured. So depending upon our skill, we basically choose the type of machine, and also on the complexity of the fluid domain. If the domain is simple, we can go for the structure. But if the domain is complex, it is very difficult to make structure there. So then, in that case, then we go for the unstructured machine. Generally, meshing software automatically they make a unstructured mesh. So for making a unstructured mesh is not a challenge. All meshing software automatically provide this, but you need to see the quality there. But to make the hexahedral mesh, that is the art. In academics, people are basically using the hexahedral mesh so that their publications can be easily done. Because unstructured machine, you don't need to do anything. Whatever the this software will do, that will you will get. But to make the hexahedral mesh, that is the art. Nowadays, people are working on this, and those who make the structured mesh, their demand is very high. So this is not any fluid mechanics thing. It is just a art. How artistically you make a mesh, and how much you can control the quality there. So that is the real thing. Okay. But the advantage the structured mesh has, once you go for the structured mesh, the number of the mesh count will get reduced. So 20 years back, where the computational facility was not that much high, people basically do the structural is less number of the mesh, and you basically control the quality. This quality you can see different kind of quality. You can see this something is okay. I hope that it is visible to you.
Yes, sir.
Okay. So here you can see that this is the unstructured mesh, tetrahedral mesh. Here you can see this mesh looks very excellent because all the dimensions are in a ratio is good. But here you see this length is very small. So this mesh is not good. So once you are doing the meshing, the quality is very much important. Here we are talking about the skewness. This is good. This is something in this range. This skewness is very bad. So this length is very much less than these three lengths. So sometimes there is an error in the meshing. So that you have to be more cautious there, that you should make a good quality mesh. Now, this way you can see how we decompose the different domains in casing. This is the guide vanes, then runner and draft tube. So you can see kind of the mesh count we have here. So generally in the hydro turbines, we make a mesh in the order of crores, 10 millions, 15 millions, 20 millions, like that. This is the one example where you can see the kind of the mesh quality and the kind of the mesh node, number of node and element you can see here. That's required a lot of computational power. This is another case of the turbine. Now, once we apply the boundary condition, we get these kind of the streamlines. Here you can see this region, the streamline is disturbed. So we can see we can see a lot of because this is a draft, and draft you section, and once the flow is changing their path, a lot of disturbance takes place. So we have to make this part draft tube elbow section that should be more streamlined. Then only we can get the maximum performance. So I basically focus on this part, and I redesign this part, and I propose a new file of the draft. These are some residual you can see through the solvers. These are some transient. This is the arc, and you can see that particular point, best efficiency point. See the addition torque we have. So you can see what kind of application is the mean, then you can see plus minus how this torque is being calculated. So that what is the fluctuation there? Different design of the fluctuation. It is more dependent upon the in my research, what I do, I just got a velocity profile at the inlet of the draft tube, and I varied the design of the draft tube. I varied the design, and then I made okay. I discuss this thing in the later part. Here you can see this kind of the fluctuation in the efficiency you can get. This is the fluctuation of the net pressure. This is the fluctuation of the torque. So once you do the transient analysis, you can get the average transient value, the fluctuations, and that is the useful information with respect to the life of the turbine. Now you see at different operating conditions, best efficiency point, part load, overload is the existing. This is the existing draft tube where you can see the elbow section is not well designed. So in my research, I have focused on this elbow section so that this section need to be more streamlined. And to quantify this recovery and loss factor. These are the two factors which I have focused, and I redesigned this shape. Once, and this redesigning, I have used the RSM, response surface method, and I have taken into account 8 geometrical parameters relevant to that elbow section. So we basically vary that particular parameter, and we found out the best possible profile. Here you can see this green one is the existing one, which is like this, and the red one is the case where we have just allowed to more draft tube height. This is the setting height somewhere here. So in that case, we allow 10% more height of the draft tube. In the black one is more streamlined by using the same height of the draft tube as the existing one. So here you can see this is the existing one where there is a sudden change in the area in the elbow section. You can also visualize this. Here there is a sudden change in the area, cross-sectional area. So once the fluid is changing their path, you have to control this area. This variation in the area should not be exponent. Here you can see this is exponential variation in the.
Yes, sir.
If you have, please let me know.
Sorry, sir. Sir, can you please repeat?
Any questions if you have regarding this discussion? You can. Now the forum is open for the discussion. Anyone would like to ask any question?
You can also write your question in the chat box.
Any question?
Thank you, sir. Thank you, sir. Actually, sir, we are aware that the CFD are very much prone to the convergence issue and they require really good mesh. Sir, I want to ask you, sir, how will we decide the number of modes and elements during meshing, sir? Because it is very case sensitive thing.
Actually, for doing this, we have to do the grid independency test, where we have to make the 2-3 different kind of the dense, coarse, and the very fine mesh, and then we have to do the simulations, and we have to see how the output parameter is sensitive with the mesh density. Suppose if you are doing this, suppose just I take example here. So suppose if you are making a mesh of this particular any turbine, so you make a mesh of suppose 2 million nodes, then 4 million node, and 10 million, 20 million. Suppose four different kind of the mesh density mesh you have. Then you do the simulation and you see how the output parameter, suppose output parameter here is efficiency, how the efficiency is sensitive with the meshing number of node. Suppose at level 3, suppose 10 million node. After that, if you are making more node, the efficiency is not going to change. Then you can say this 10 million node is the optimum number of the node. Okay, because if you are making more dense mesh, the result on the output, the effect on the output parameter is not significant. So that we decide the optimum number of the mesh for different application. In hydro turbines, generally, optimum number of the mesh will come like 20 millions. Different applications, it may be different. In some simple application, the optimum mesh count may be 1 million or 5 million. But in the hydro turbine, generally, optimum number of the mesh count comes in a range of 10 millions or 50 millions. So this is being decided using a. I hope that answer is clear to you.
Yes, sir. Sir, we
And
have another question.
Thank you, sir.
Okay.
Sir, Hitesh sir has asked, what is fluid structural information FSI?
Okay, generally we do the CFD nowadays. Up to now, we do the CFD analysis for the hydrodynamic performance, for evaluating the hydraulic performance. But the hydraulic performance is not enough for the design parameter. Suppose your hydraulic performance is good, but if your structural performance is not good, the design will not survive. So nowadays, what the people are doing, they are basically coupling the CFD analysis with the FEM analysis. So the live data which we get from the CFD analysis, that is being taken into the FEM analysis. Okay, generally if you do the FEM analysis separately, you have some input condition, some fixed input condition. But using CFD, you get the whole information of the pressure distribution. That whole information of the pressure distribution will go as an input condition for the FEM analysis. Okay, so that's why once you couple the CFD with FEM, that study is called the fluid structural interaction. So that is a very burning topic nowadays, where we simultaneously predict the hydrodynamic behavior as well as structural behavior of the system.
Thank you, sir. Sir, we have another question. Suppose Manish sir has asked, suppose if we choose any shape other than sphere, will slip happen?
Other than sphere,
If we choose any shape other than sphere, will slip happen?
will, pardon,
Sir, slip, S-L-I-P, slip.
Philip, I don't know what meaning of Philip here, but yes, any shape. Suppose if you are putting a plate there, so the plate once any restriction if you put in the path of the fluid, so ultimately it disturb the distributions there. So if the express is there, the wave formation will be different. If the plate is there, wave formation will be different. So the idea here is, because all the informations you cannot get using the experimental techniques. If you are going for experimental techniques, then you have to install the sensor at different locations, only you get the information. But using the CFD, you get the information at every point. So this is example. You can put any shape there. The disturbance will be different. The wave formation after the object will be different. For sphere it will be different. For cylinder it will be different. So it depends upon the what kind of the object we have put on the path of the flow. So simultaneously the distribution gets changes.
Okay, sir. Sir, we have last question here. Manish sir has asked, why flow is incompressible when velocity is equal to or more than 20 meters per second?
Actually, this condition we justified with the Mach number. If the Mach number is less than the 0.2, we generally consider that flow as a incompressible flow. Mach number is the ratio of the velocity of the flow to the velocity of the flow, velocity of the sound in that medium. So generally, the velocity of the sound in the medium is around 300 meters per second. So if the velocity is 30 meters per second, then only we consider the flow as a compressible flow. But generally, in the hydroturbine applications, velocities are in the range of 10 meter to 20 meters. So generally, that's why it is written there that the flow is incompressible flow.
Sir,
Basically, Mach number is less than 0.2.
Okay, sir. Thank you, sir. Sir, last question is, sir, can you please guide us more about HyperMesh software apart from the ANSYS? How analysis is different from HyperMesh?
Oh, HyperMesh is also a useful tool. It depends upon, because the strategy is same. The ANSYS is the name of the company, and basically in that platform there are number of software for the simulation, number of software for the meshing, number of software for the modeling. So it depends which company is basically taking over which kind of the software. So it is nothing but the thing. But the thing is, every meshing software, the approach is simple. We have to decompose our domain in such a way that the quality of the mesh will be within the reasonable limit. The approach is same. Whether we go for the HyperMesh, whether we go for the ICM CFD, lot of the softwares are there, like COMSOL is there, number of softwares are there, number of companies are there, number of softwares are there. It depends in which software you are more comfortable. So strategy wise, there is a no difference. Like the simulation, we have two software for simulation, CFX and Fluent. The thing is, both do the same thing, but the Fluent is more means equally good for the other applications also, apart from the rotating kind of the problem. But CFX is very good for the rotating kind of the problems, where the some rotor is rotating and some kind of things. But the heat transfer, basically the Fluent is very good, because the Fluent is a very general software, and CFX is very much more relevant for the fluid flow applications. So it depends, but the whatever software we choose, for me, get the accurate result. So it depends, because a lot of time people do the ICM CFD for the meshing. Once we are once we are going for the structured mesh. Sometimes the ANSYS workbench, this ANSYS meshing is enough for the making the mesh. So it depends in which software you are more familiar, and the ultimate point is we have to control the quality.
Sir, we have question from George, sir. Can you please throw some light on how uncertainly quantification is done in this case?
Okay, so there are two approach. There is a Richardson method, which we basically use to quantify the numerical error. So in the numerical error, which includes the, like we basically what we do, we just decompose the second order differential equation into the algebraic form. So in that decompositions, we basically discard the higher order terms. So there we have the a lot of the means higher order term we are neglecting. Then there are some uncertainty. There are some uncertainty related to the round off error. There is some uncertainty related to the convergence, because in CFD what we do, we just apply the some convergence limit, that up to this limit we are going to stop the iteration. So a lot of the things is there which basically incorporate in the uncertainty analysis. But quantification wise, Richardson method is there, quantification of the uncertainty in the CFD analysis. And that doing the Richardson analysis, there is a well-defined procedure there, where we have to simulate the three cases: fine, coarse, and very fine. Then we see the how the output is being sensitive to these the mesh density. Then we get the quantification. So that is the well-defined means approach, and mostly 99% of the paper which is being accepted in this area, there the reviewer want to see the Richardson method analysis. One method we qualification wise, we have the grid independency test, but the quantification wise, we have to follow the Richardson method. So I hope that I could get some light on this.
Thank you so much, sir. Sir, at last, we have a request. If you can share your PPT with us, it would be grateful for the participants.
Sure, sir. Sure, sir. After this, I just send this PPT to over the email, and you can distribute it.
Thank you so much, sir. Now we have come to the end of the session. We would like to convey our heartiest thanks to Dr. Ali Abbas for such an exciting session. This was a supreme paradigm of why this kind of interaction is crucial. We are thankful, sir, for enlightening us. Thank you so much, sir.
Thank you, all the participants for this patiently listening the lecture, and I am thankful to Sharma sir to basically.
Thank you very much, sir. Thank you very much, sir.
Opportunity to me.
Thank
I'm very
you, sir.
thankful to you. Okay, sir. Thank you very much.
Thank you. Thank you.
So from tomorrow we have sessions from 9:30. So it will be great if you join from tomorrow onwards. Thank you so much. Let's see you tomorrow.